Center for the Ethiopian Educational Information and Communication Technology presents Educational Satellite Television Programs.
Hello, teacher. Hello, students. Welcome to today's lesson on matrices and determinants. Today, we will study systems of equations with 2 or 3 variables. We will learn how to find the associated augmented matrix of an equation, as well as how to perform elementary operations on matrices. Students, let us begin the lesson. Matrices are most useful in solving systems of linear equations. Systems of linear equations provide mathematical models of electrical networks, traffic flow, and many other real-life situations. An equation, A1 times x1 plus A2 times x2, and so on, equals B, where A and B are constants, and x is a variable, is called a linear equation. A coefficient matrix for this equation has a column of A1, A2, A3, and so on, and a column of x1, x2, x3, and so on. A coefficient matrix is the matrix formed by the coefficients in a linear system of equations. In this example, you can see how the coefficients from the linear equation form the coefficient matrix. An augmented matrix takes the coefficient matrix and adds an additional column for the constants on the right of the equal signs. The new column is at the far right of the matrix. Here we see a system of equations. Matrix A represents the coefficient matrix. Matrix B represents the results. An augmented matrix is represented by A/B as shown here. We can see the additional column of the constants to the right of the vertical line. Students, please take out a piece of paper and try this activity. I will provide you with 3 systems of equations. Give the augmented matrix for each system. You may begin the activity now.
Students, Let's get ready. Begin. Time's up. Let's get back to our lesson.
Welcome back, students. If your matrices looked like these, then you are correct. Here is the matrix for the first system. Here is the matrix for the second system. Finally, here is the matrix for the third system. Did you remember to put in a 0 value for the Z column of the first equation? Good work. You can find more examples of these matrices in your textbook on page 247. Two systems of linear equations are equivalent if and only if they have exactly the same solution. Students, please look at these two systems of equations. Are they equivalent? Please try to solve the systems for the values of x and y.
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Hello again, students. How did you do? I am sure that you remembered how to solve systems of linear equations from your previous lessons. We can use the elimination method to solve these systems. If we add the equations in the first system, we can eliminate the y variable. We are left with 2x equals 6. When we solve for x, we get x equals 3. If we substitute 3 back into the first equation, we find that the value of y is 2. So the solution for the first system is x equals 3, y equals 2. When we add the equations in the second system, we can again eliminate the y variable. This leaves us with x equals 3. By substitution, we find that y equals 2. Since the solution for both systems is x equals 3 and y equals 2, the systems are equivalent. Good work. You may recall that to solve systems of linear equations, we use either the substitution or the elimination method. The method of elimination is more systematic and can be expressed in matrix form, but this method is based on equivalent systems of equations. In order to change a system of equations into an equivalent system, we can use any of the following 3 operations. These are called elementary or Gaussian operations. The first method is swapping. We interchange 2 equations of the system. The second method is rescaling. We multiply an equation of the system by a non-zero constant. The third method is pivoting. In this method, we add a constant multiple of one equation to another equation of the system. Students, you have already learned how to write linear equations as augmented matrices. Do you know that you can perform the 3 elementary operations on these matrices as well as on linear equations? In fact, you can perform these operations on either the rows or the columns of the matrix. When you perform the operations on rows of a matrix, they are called elementary row operations. You can swap a row by interchanging 2 rows of a matrix. You can rescale a row by multiplying a row of a matrix by a non-zero constant. You can pivot a row by adding a constant multiple of one row of the matrix onto another row. The same operations apply to columns of a matrix. They are called elementary column operations. Because each row of an augmented matrix corresponds to a linear equation, we will use elementary row operations only. We have covered a lot of material today, students. You have learned the difference between coefficient and augmented matrices. You have learned how to turn a system of linear equations into an augmented matrix. And finally, you have learned the three elementary operations that can be performed on a matrix in order to calculate equivalent equations. In our next lesson, we will study how to apply these operations on augmented matrices. That is all the time we have for today. Until next time, thank you, teacher. Thank you, students.